everyone. Welcome to this special session named the Acoustic Echo Cancellation Challenge. I'm very pleased to give this presentation. My name is Peng and I come from the Institute of Acoustics, Chinese Academy of Sciences. The title of my paper is Acoustic Echo Cancellation using Deep Complex Neural Network with Nonlinear Magnitude and Phase Information. Here is the contents of my presentation, including background of the AEC problem, existing solutions, method proposed in this paper, and we show the results and conclusions at last. Traditional linear and time environment echo model is shown in the right figure, where Dn is the microphone signal, Rn is the reference signal, H1n is the impulse response of the acoustic echo path. Sn is the near and target speech signal. When we consider the hands-free tight conference scenario, the impulse response H2n from the target speech to the microphone cannot be ignored anymore. Vn is the environmental noise. The core idea behind the traditional acoustic echo cancellation algorithm is to estimate the echo signal using the adaptive filtering theory, which achieves great success in the last 40 years. Although the great success of the linear AEC algorithm, there are many factors that can degrade the performance of the AEC algorithm. Among the most is the nonlinear of the system, including the nonlinear of the loudspeaker, the nonlinear of the microphone, and so on. Nonlinearity makes the linear AEC algorithm unmodeled. The second is the time variation of the echo path in realistic applications. The third is the double talk scenario, where the near speech signal can disturb the convergence of the optimal filtering. The fourth is the large time delay between the reference signal and the microphone signal. This is especially the case in real-time teleconference system due to numberless buffers related to coding and decoding. All the above-mentioned factors cause the common residual echo problem. Besides the residual echo, linear AEC algorithm cannot handle the environmental noise and the near-end reverberation. So, in realistic applications, linear AEC algorithms are rarely used singly. Instead, they are often used with post-processing. The first type is the linear AEC algorithm with traditional post-processing, which is shown in the figure. The post-processing module may or may not use the reference signal, while the residual echo is treated as one type of noises and is suppressed using the statistical models. The second type is the linear AEC algorithm with deep learning-based processing, where the deep neural network is designed to directly map the error signal to the near and target signal. This type of method shows promising performance in realistic applications and achieves the best results in the previous ICASP AEC challenge. The method proposed in this paper also belongs to this type of method. The third type is total deep learning-based processing without the linear AEC algorithm. Here is an example of the deep learning-based acoustic echo and noise suppression method proposed recently, where both the reference signal and the microphone signal are directly mapped to the target signal using a convolutional recurrent neural network. As mentioned in previous slide, the method proposed in this paper consists of two parts, including the linear AEC algorithm and the deep learning-based post-processing. I will introduce the network structure first, because the network should be trained at the very beginning. The network structure is the modification of the gated convolutional recurrent network originally proposed by Peng. We add a convolutional layer with 1x1 kernel size and 1x1 stride in add-skip connection between the encoder and decoder layers instead of concatenate skip connection, which can greatly reduce the number of input channels of the decoder layer with slightly performance degradation. The detailed settings of the proposed network is listed in this table, where T denotes the number of time frames in the spectrogram. It should be noted that we set the kernel size around time x to 2, which means 2 time frames are used simultaneously in one convolution, and we strictly use the current frame and one previous frame to do the convolution. So there is no additional latency introduced by the network computing. Two datasets are provided through the challenge, where one is synthesized data and the other is real recording data. Because there is no clean speech in real recording dataset, it is not suitable for constructing the training datasets without additional processing. For the synthesized dataset, we found that the amplitude of the near-end speech is different from that of the near-end microphone signal due to the automatic gain control. So gain normalization should be made on the near-end speech beforehand to construct the target speech. The far-end reference signal and the near-end microphone signal are used in a linear AEC algorithm, which we chose the PBFD LMS algorithm to cancel the echo signal and obtain the error signal. To improve the generalization capability of the proposed network, we expand the dataset by synthesizing the reference signal, the microphone signal, and the target signal by ourselves, using the system signal model. It should be noted that both the reference signal Rn and the near-end source speech Sn are randomly chosen from the clean speech dataset. Both the imposed response H1n and H2n are randomly chosen from the IRR dataset. It should also be noted that we chose the near-end speech with early reverberation as the target speech, which makes the network have the ability to suppress the late reverberation and the environmental noise simultaneously. After constructing the dataset of the reference signal, the error signal, and the target signal, all the signals are transformed into the frequency domain using a short-time Fourier transformation with a frame length of 20 milliseconds and a frame shift 10 milliseconds. We use the square root of the magnitude to reconstruct the complex spectrogram as both the input features and output features. Because this type of compression is quite suitable for speech reverberation, as we found in our previous work, it should be noted that we reconstruct the real and imaginary parts of the far-end reference signal using the phase information of the error signal, which can improve the robustness and the time jitter of the far-end reference signal. The MMSE loss function and the ADAM optimizer are used in training this network. For the brand test dataset, we found that the time delay between the reference signal and the microphone signal has a large dynamic range, which is shown in the left figure. It can be seen that most of the time delay ranges from 0 milliseconds to 300 milliseconds. The largest time delay can be as large as 1.8 seconds. So we proposed to use 4 parallel PBFD LMS algorithm, where the reference is delayed consequently in each unit to cover this large dynamic range of the echo delay. It should be noted that there are several samples that the echo signal in the microphone is ahead of the reference signal, which cannot be well handled by our model. According to this challenge rule, all the processed brand test datasets are sent to the organizer to do the noise evaluation according to the ITU recommendation. And here present the official noise results. It can be seen that the proposed method can greatly improve the speech quality in the listed 4 scenarios compared to the baseline. We also conduct the degradation noise evaluation and the echo noise evaluation using the DEC noise tool provided by the organizer. The results are shown in Table 2 and Table 3, where original represents the microphone signal, PBFD-LMS represents the error signal, and GCCRN represents the algorithm proposed in the ICASP AEC challenge by our work. Mu represents the movement scenario. It can be seen that the proposed algorithm in this paper achieves the lowest degradation noise score and the highest echo noise score in different scenarios. The spectrograms of the near and microphone signal, the selected error signal processed by the 4 PBFD-LMS units, and the output of the proposed GCCRN model are shown in this figure. One can see that the acoustic echo can be partially suppressed by the PBFD-LMS algorithm, while the near-end speech remains undistorted, and the proposed model can well suppress the residual echo. Besides the residual echo, the proposed GCCRN model is also able to suppress the environmental noise and late reverberation efficiently. In the end, I would like to summarize our work. First, we proposed to use 4 parallel PBFD-LMS units to cover a large dynamic range of the echo delay in the blind test datasets. Second, we proposed to use the modification of the GCCRN network to suppress the residual echo, late reverberation, and the environmental noise simultaneously. The third, we proposed to use the square root of the magnitude to reconstruct the complex spectrogram to train the network. And I will end my presentation with thank you. Thank you for your listening.
Thank you. Thank you for the nice presentation. Again, if people in the audience have questions, please type them in. I can start with a similar question that I already asked previously. So you also use the complex spectrum in your networks.
Yes.
Have you checked what's the impact of using complex versus magnitude only?
The complex magnitude or the complex feature can restore the clean speech. If you just reconstruct the magnitude but use the phase information of the original microphone signal, it can the phase information is correct, it's wrong, and cannot reconstruct the clean speech. So we use the network to construct both the real and the imaginary parts of the target signal.
Mm-hmm. Did you also happen to do like a test or a study? What's the most impact, for example?
Oh yeah,
for PESC or
this feature has been done by extensively by Peng. Actually, we follow the work done by Peng. The complex spectrum is originally proposed by the team.
Thanks. So we have a question from the audience. Which loss function was used to train the neural network?
We use the basic MSE loss function of both the real and the imaginary parts.
Mm-hmm.
Yeah.
Other questions?
Yeah, I have a question. So I think you said that this model has 10 million parameters.
Yes.
Did you try to do any type of optimization to reduce the number of parameters like some type of pruning optimization?
Actually, after this challenge, we have already reduced the parameter to about 2.4 million parameters, and the performance is quite similar to the large model. So I think this can be done in the future.
Okay. How did you do the optimization? Is that by pruning, or can you elaborate on how you reduced it from 10 million to 2.4?
We just reduced the input channels in each layer.
Okay.
Yeah.
Okay. So kind of a manual structural pruning.
Yeah.
Okay.
All right. Seems there are no more questions. So thank you, Renhua, and let's move on.